Okay, today we're going to be speaking, as you said, about various vulnerable conditions that exist in modern software, both applications and operating systems, and how to detect such conditions. We're going to be speaking about both Unix and Win32, but pretty much a heavy accent on Unix, as Win32 applications tend to be closed source. But we will be touching on it because a lot of the concepts actually apply even if you don't have the source code. We're going to be concentrating on popular APIs in both types of operating systems, as well as a couple of dangerous error conditions that programs are prone to when using C++, which is the type of code we generally audit. We'll each be describing vulnerabilities and showing demonstrations and source code from real-world applications to give people a better idea about how these vulnerabilities actually appear in practice. Some of the examples we're giving out, all of them have now been disclosed, but the latest one was actually disclosed today, so it might not yet be widely known here. A lot of papers, so we decided to do this because a lot of papers have been brought out on BugTrack and stuff that basically describe in detail how to exploit buffer overflows, various different types, stack-based overflows, and also techniques for misusing malloc implementations to gain control of a process, and even like writing shellcode for different architectures with tips on how to eliminate null bytes and stuff. And these are all really valuable, but in order to exploit them, you actually have to be able to find the bugs in the first place, which is why we chose this topic rather than exploitation techniques, because in the past, bugs were pretty easy to find. You just had to like grep for a string copy routine or something, and it was not much of a science. But now it's a lot more difficult to locate some more subtle bugs, and the auditor must often understand the logic and mechanics of the program that he or she is analyzing. Please note that this speech isn't definitive. Finding security vulnerabilities is really limited to the auditor's imagination, really. And so what we cover here is only a subset of all possible vulnerabilities. There's also some other types that we know about and stuff, but we can't fit it all into this speech. This is going to be, we're going to basically divide the speech into a couple of different sections. We're basically going to firstly present methodology of how you go about attacking a large code base to find vulnerabilities, and then we're going to talk about various classes of bugs, and as well as tools of the trade. The main types of class of bugs we're going to talk about are dangerous library and API functions. These are pretty well known, as we said before, so we're not going to spend long on this. Then we're going to also talk about unsafe use of pointer arithmetic, subtle trust relationships, and also integer manipulation issues, which have been a lot more prevalent recently. So we're going to go over to methodology now with Neil.
Okay, so in order to find bugs in large software programs, you need to have a planned method of going through them. I mean, you can't just randomly read them and hope to stumble upon a bug. And so we've tried to split it up into 3 different methodologies. The first one I'll talk about is the top-down methodology, where you start at the program entry point and you read through each and every relevant code path, and you try to understand the larger scope of the program and how every API interacts, and you want to get a very deep understanding of the internals of the program so that you can spot very subtle bugs. The thing about this is that it can take a lot of time, and it may not be necessary to go into that depth to find certain bugs. So another way to go about it would be to try a bottom-up approach, where you look for dangerous APIs or what looks like really messy code, and you trace backwards and see if there's a potential for a vulnerability there. So you'll spot more obvious bugs this way quite easily, because obviously it'll stick out that, well, he's doing an sprintf here, or he's, well, we'll go into that in more detail when we discuss the actual bugs, but you're going to miss a lot of subtle stuff and a lot of stuff that requires a deeper understanding of the knowledge of the program you're analyzing. So a hybrid approach sort of incorporates the best of both worlds, where you might go and look for potentially dangerous places within the code, such as anything that processes user input, anything that does parsing, anything where a programmer might make a potentially fatal mistake. And then what you try to do is to understand that part of the code in depth and trace forward and determine whether or not a vulnerability exists. It's a more focused approach. I like this one better, and it'll save a lot of time while you can still find some very nice bugs using this. Some other things that are helpful is basically you want to be able to keep track of all the necessary conditions to create a vulnerability. So what I tend to do when I audit is to create a list of requirements for this vulnerability to be triggered, and then go ahead and trace through the code and check them off, saying, well, yeah, this variable can be this value at this point in the code. So yes, we do have an overflow here or whatever. And that allows you to go ahead and verify that a vulnerability does exist without actually going and trying to write the exploit. Another thing that is quite helpful is to understand the way the programmer is thinking when he's written this code. If you notice a tendency to use or to do very sloppy pointer arithmetic, or to use unsafe functions in a lot of places, you might want to focus on that instead of focusing on looking for something else like integer overflows within the code. And so you cannot kind of understand how the programmer is thinking when they're writing this and what you might want to look for. In terms of tools, you don't really need complex or advanced tools to audit source code. It comes down to understanding and analyzing the source and being able to think of something that the programmer completely missed. So there are things, however, that will help you in this process and make your life a lot easier. In terms of auditing, you spend a lot of time in a text editor and staring at source code there. So picking a good editor is pretty critical, something you're comfortable with. I like to use Vim. It has some features that actually help you quite a bit when auditing. Syntax highlighting is okay, I guess. If you can't spot stuff like variable definitions, and maybe you shouldn't be auditing code, but it makes it easier to look at. Something I find useful is bracket matching. If you're looking at a complex code branch and you'll see maybe 5 or 6 brackets open up and you're trying to track down where one closes, this can help you just to understand the flow of the code. C tags is also very useful because you can navigate the source code quite easily from within the editor and jump to the definitions of functions or variables quite easily, rather than trying to exit your editor and going and trying to grep the entire source tree, finding out where this function is or whatever. So Vim has all those features. Emacs, it has all those and probably a million more. It's pretty big. I'm sure you've heard all the jokes about the acronyms for Emacs, like, I don't know, 8 megs and constantly swapping, or all those stupid jokes, right? So, and Pico has none of these features, and it never will, so don't use that. Source browsers are pretty useful too. I think Source Navigator runs on a variety of platforms. I've seen it on Windows, and I believe it compiles on Linux too, so it's quite useful. You can actually sort of navigate through the source by following where functions go and tracing from one function to another and so on. So it's quite useful. My personal favorite is cscope, and I use that a lot. You can use it to recursively search a very large source tree. I think I tried something like a 300 megabyte source tree the other day, and it had no problems whatsoever, so it's quite robust. You can locate the definition or the use of any C symbol within this large source tree. So if you want to find where a variable is defined, you can go ahead and look at that, or you can find all instances in which this variable is accessed, used, whatever. So that's very useful. You can track all locations where a function is called, or all the functions called by any specific function. So that's quite useful. And what it'll do is it'll give you a list of all the references found, and then you can invoke your editor and go ahead and look in greater depth there. I'm sure a lot of you use this, and it's pretty good. There's some plugins for different editors where you can invoke cscope from within the editor. So that'll make your life a little easier. cbrowser is a graphical front end. I think it's TCL/TK for cscope. So if you like graphical user interfaces, give that a try. And there's some automated auditing tools out there. I really don't like them. I think they suck. If you try them out, they'll find some things, but some of them are basically just grepping for sprintf and string copy and whatever. Some of them go into greater depth. You might want to try out Splint. Has the ability to find some complex bugs, but it can't analyze the more complex logic bugs. And SQL is, I haven't actually been able to try that out, but some people tell me it's pretty good. And just one other thing that might be useful, a lot of vendors offer a CVS web interface to their source tree. And so you can go there and track recent changes in the latest releases and see when they patched this, or if they have, what subtle changes they're trying to slip by without doing an advisory on or whatever. So sometimes that's quite useful. And I think that's it for tools and methodology. Most of the ones I talked about are free. I think you have to pay for ITS4, but everything else I mentioned they're available free, and most of them are open source.
Source Insight is very good.
I haven't heard about that.
Okay, we're just going to move on now to dangerous libc functions. These have been covered a lot in the past, but as we said, we're going to just have to go over them for completeness' sake. We're just basically going to quickly mention two classes of functions. One is unbounded memory copies, such as string copy, string cat, sprintf, esprintf, all that kind of stuff. As you know, if you've got a source buffer that's, you're copying source data that's got more data than can fit into the destination buffer, then you can influence the state of the program and the execution flow, and often get root access or execute arbitrary code. To combat these problems, a while ago there was bounded memory copy functions that were introduced. These were meant to eliminate the problems inherent with the previously mentioned functions. They usually take an extra parameter denoting the maximum size of the destination buffer, but it later became apparent that some of these functions were also quite misleading and could be used to cause buffer overflow conditions as well. We're mainly talking about these kind of functions, which have also been covered in reasonable depth in the past. The first function we mention here is string copy, which has the problem that if the source string length exceeds the maximum size of the destination buffer, then the destination buffer would not null terminate the string, which, although doesn't seem like too much of an issue, problems can arise when programmers attempt to append a null, which can result in a 1-byte overflow, which has happened reasonably frequently in the past. Copy the string into another buffer of the same size, often resulting in a 1-byte overflow, or copying or concatenating the string into another buffer when another string buffer is in an adjacent memory location, thus forming a larger buffer. The second function, strncat, has similar problems, but in many situations is more dangerous because it's misleading for 3 reasons. Firstly, the size argument for string strncat doesn't account for the trailing null. Firstly, there's the misleading size value in strncat, which is basically, it looks like it should be the size of the buffer that you give as an argument, but it's actually the remaining length in the buffer. There's actually strlcat now, which fixes this problem. Secondly, strncat doesn't account for the trailing null byte when processing the size value, so you actually have to pass the size value as the remaining length -1 so that strncat won't append a null byte past the end of the buffer. And there's thirdly potential underflow problems when addressing the trailing null issue. Basically what that means is if you've got a buffer that you can make the string length of the buffer the same as the size of the buffer, you can often cause the size argument to underflow because often the size is calculated dynamically, and it'll usually be like size of buff minus str len buff minus 1. So if size of buff and str len of buff is the same thing, then -1 will get passed to str ncat as the size value, which will be cast to a huge positive value because it's a size t type. And finally, there's misuse of return values in snprintf. Basically, that's just referring to the fact that snprintf and vsnprintf actually return the number of bytes that it would have written into a buffer rather than what it did write, what it would have written if there was enough room. And programmers often sometimes make the assumption that it'll only return a maximum of the size of the buffer, but we'll talk a bit more about that later. So there's a few quick examples of the 3 strncat problems. The first one is the remaining length issue. As I said, it seems logical that you should give the size of the buffer for the third argument, but that's actually not the case. So in the example up there, this will actually overflow by the length of the first string that's copied into the buffer. The second is the off by 1 problem I mentioned. As I said, you've got to account for an extra byte because strncat will always append a null and doesn't account for it with the size value. So in this example, it looks like they're accounting for the size, but they're actually off by 1 and can cause a 1 byte overflow here. And the underflow issue that I talked about is basically, if you can make size of buff and str len buff the same value, which often happens if you've got a strn copy immediately preceding an strncat or something like that, when there's no explicit null termination. So yeah, we'll move on to pointer arithmetic now.
Okay, pointer arithmetic. Okay, memory management is a pretty important issue in C, and has accounted for a large number of programming errors which have led to remote compromise. Basically, manipulating sections of memory arbitrarily alters the state or logic of the program. We therefore need to address pointer arithmetic and show the impact it has had on software security in the past. In this section, we will examine the following issues: looping constructs, miscalculations, and off by 1 errors. Okay, first example, we're going to look at NTPD. As you can see here, there's a loop here fails to terminate at the end of the buffer, resulting in a buffer overflow. This is often caused by failing to terminate the loop when reaching the last available place in memory of the destination buffer, and in the case of strings, terminating on a null byte instead. Although this seems like an obvious error during complex parsing routines, it can be quite hard to avoid. And you see just here you've got the star TP++ equals star CP++, and that's only going to terminate when it encounters a comma, a dash. Fuck. Okay. Looping constructs, LPD. This is a char pointer overflow. This kind of mistake has been made a few times in the past. This bug is not immediately obvious as the one shown previously. However, it can be seen that, like the other bug, the end of the array can be reached without the loop being terminated. It's just a while loop here. Oops. Nice. Okay, you you've basically got an array of pointers which is filled with STR dupe, and that's processed every time there's a opcode of 3, and you basically just have to overrun 64 elements in that array.
We had to cut a lot of the code out of that example because it didn't fit on the slide, but that's actually in a while loop reading user data, so it basically gets a user string and decides what to do with it, and there's a couple of different cases that we had to cut out, but basically you can send as many names as you want and overflow a string array, and that's what that df list line is all about. That's what causes the problem.
Miscalculations. Sometimes when performing a pointer arithmetic, miscalculations can be made as to how much space is left in the buffer. This can allow for malicious attackers to sometimes write outside the bounds of the destination buffer. And the bind 8 tsig bug was an example of that last year. Okay, off by 1 errors. In the previous examples, large buffer overflows were occurring due to failure to recognise the end. Sometimes though, when calculations are done a little more carefully, termination can occur at the end of a buffer. However, there are quite often off by 1 errors, which 1 byte too many or 1 too many data elements are written to a buffer. And this is an old example from OpenBSD, FTPD. The pointer just points outside the bounds of the buffer after that for loop, and a null byte is written. Exploitation of this bug depends on what variable you can overwrite, or if you overwrite some save state information, typically the low byte of the base pointer for Intel stack based 1 byte. It also depends on the buffer size. If the buffer size is an odd number, or often not a multiple of 4, the buffer will be padded with extra bytes for optimization reasons, which renders the bug unexploitable. This happens sometimes when operating systems declare common variables with odd numbers, like max path length as 255, or a buffer declared as buff max length line +1. Okay. A lot of pointer arithmetic bugs can be quite subtle and difficult to spot, especially in programs that keep multiple pointers pointing to the same buffer, or attempting to keep save locations in buffers and doing a lot of memory copy operations. Buffer overflows that occur as a result of pointer arithmetic bugs most often occur in one of the following situations. Got the off by 1 miscalculation, as previously discussed. Errors often occur in looping constructs when 1 too many iterations is performed, or a byte is appended after a bounded loop, usually a null byte. Similarly, pointer variable can be incremented to a point 1 byte out of the buffer, which might be useful to not only write an extra byte into the buffer, but also to underflow the length variable. Here's an example. This looks okay, like terminating the string after 123 bytes, and you're just using a string end copy to copy the user data in. But the problem here is pointer is incremented outside the bounds of the buffer, and then when you have this length calculation, it's going to underflow, and a -1 is going to be passed as a size argument to the next string end copy. Okay. Next one is excessive pointer increment. Incrementing a pointer too far. This is like the last scenario, except the pointer is incremented multiple bytes past the end of the buffer. This may occur due to unexpected return values from a function, or misinterpretation of length remaining in a buffer. We'll look at this example for SNPrintf functions. They return the number of bytes that would have been written if enough buffer space was provided in the destination buffer. However, programmers sometimes assume that these functions only return the maximum number of bytes they have actually written, resulting in bugs such as this.
That was also operated system benefit about 4 different behaviors.
Yeah, well, yeah, okay.
One of which is return -1, it won't write hide.
Yeah.
The more modern behavior is to return the amount of data it should have written if there was enough space left in the buffer. But old implementations return -1, and you'll see that in a lot of older code still.
Okay. The first SMPrintf looks fairly safe. Just writes data to the buffer, but it increments a pointer way past the bounds of the actual buffer. And the next SMPrintf underflows with the length specifier due to the calculation. And yeah, that's obviously a problem. Okay, next thing is union mismanagement.
Okay, I'll just very briefly go over this. I'm sure most of you know this. A union is a data structure in which the elements overlap in memory. So here we have a union with an integer, a short integer, and a character pointer. And the size of this data structure is actually 4 bytes on a 32-bit architecture. So the fact that these elements overlap in memory can lead to some potential security vulnerabilities. Basically, the problem that can happen here is that you mistake one data member for another, and can lead to type confusion. You might mistake an integer for a different integer, which might be limited to a certain range of values, or you might mistake an integer for a pointer, and that can have some interesting consequences. I'm just going to show an example here of a potentially vulnerable application, and very briefly go over this so you can illustrate what's going on here. We have our union here within the data structure. You can't see it when it's highlighted, but we have an integer within the union and a character pointer. I hope that's readable. We have an input routine here that reads data from the user, and it's aware that it's processing a data structure that contains a union. So it properly processes the data structure and it stores it. It could be an integer, it could be a string. That's done properly. And we have our vulnerable function here, which checks the character pointer element and compares one string to what should be the correct string. If it's not correct, tries to free that string. And in our main function, all it does is it reads the data and then passes it to our vulnerable function without actually checking whether or not the value within the union is of the correct type. So what you could do here is a malicious user could send a data structure which contains an integer within that union, and it would be passed to the vulnerable function, which thinks it's a character pointer and then tries to free it. And if you can arbitrarily specify the address which you're freeing, it's very easy from there to obtain or to execute arbitrary code. I know this looks like a bit of a stupid mistake to make. I mean, obviously the coder should just check which type is present within the union, but I've actually seen this in code, and people do make this mistake. And it happens in code where the remote user is allowed to transmit data structures directly or specify quite specifically what the data structure contains. If you're trying to think about where that might happen, the thing that comes to mind immediately is RPC, and the external data representation XDR allows the remote user to transmit data structures directly, pretty much. And it's not easy to make this mistake, but it does occur in that type of code. Next is subtle trust relationships.
Well, can you guys hear me all right? Take that as yes. Well, this is actually one of my favorite classes of bugs, so to speak, for various reasons. Firstly being that it's sort of like a little job guarantee for me, because I know that these kind of bugs are never going to be found by a little monkey farm in some third world country. So Well, like my colleagues explained before, this kind of bugs actually can be found more through the hybrid or the top-down approach as opposed to the more widespread bottom-up approach, because to discover this type of bugs you need a sort of higher level analysis than what is possible through a typical bottom-up approach. Well, there are a couple of instances or a couple of subclasses of instances where this type of bugs happen, and I'd like to sort of go deeper into them with some kind of real-life examples later on, but first I would like present to you what these actual subclasses might be, and even though they may sound fairly theoretical and somewhat unrealistic, these do really happen, and these do happen in major software products. So it is something that we should not ignore when we are auditing software by any means. The first thing is that in complex software products, a lot of internal components interconnect with each other and work together to provide the actual application functionality, and there's a lot of assumptions that are made about how these internal components communicate with each other and interact with each other when it comes to the behavior, and this can be exploited in some situations by an external entity to sort of mislead an internal component into believing that it's doing something that it should be doing when it shouldn't be doing what it should be doing. And secondly, the server applications sometimes trust externally available information which might not entirely be directly related to the functionality that the application is performing at the moment, but it is indirectly related in terms of whether it's going to be some client information or some third-party token describing the client state or something like that. And another big problem which you usually see with a lot of proprietary software is that proprietary server applications with undocumented protocols tend to, probably because of sheer arrogance, I suppose, but they tend to think that their client application, which is the intended client application, is the one which is always going to access the server services and not anything else. But unfortunately, there's enough people with enough talent to reverse engineer the network protocols and write their own clients, and historically there has been a lot of bugs of this type which has been discovered. And my favorite is when people actually try to do fairly safe programming without exactly knowing what they're doing. A lot of applications try to recover from errors or gracefully terminate and deallocate resources and save debug information, logging information, and whatnot in case of an error. But the fundamental problem is that when an error happens in an application, the state of your process address space is somewhat questionable. So some of these tasks you do after an error has occurred can actually lead to successful compromisation of a system like that. And of course, that's exactly the opposite of what you want. So let's first look at internal trust relationships. Well, there are many operating systems which contain internal undocumented APIs and internal client-side libraries that are provided by the system, mostly closed source, which enable client-server subsystems to communicate, and they make a lot of assumptions regarding these methods of communication. I mean, from a simple assumption from what an API, what a parameter to an API call might be, or to a blind assumption like, oh yeah, if somebody's going to call this API, it's got to be trusted because it's our code. That's the only guy who can call it. So if you guys are familiar with one of the more recent vulnerabilities discovered in Windows NT stream of operating systems, where anybody could query handlers for a process from the debug subsystem. That's a typical example of this type of thing. And again, due to shared code base and shared development resources and same programmers programming the client and the server subsystems, it's normal that they come up with these implicit assumptions without even realizing that they're actually assuming these things about the software that they're writing. So I really tend to like these kind of bugs because they are only apparent through a very high-level analysis which tries to understand the actual process and the internal functionality of the software rather than just looking for vulnerable API calls or something like that. So even though this might sound very theoretical, there are so many bugs which is in this category in major operating systems. It's not even funny. And when it comes to trusting external information, servers tend to get information about client from either third-party sources or information that the client can directly control, which at the same time has no direct relationship to what the server might be performing at that particular point in time. For example, one of the more recent Microsoft Exchange bugs, which was released about a week back, there the DNS resolution services in the SMTP code expected any client DNS name to be within certain boundaries or have certain type of attributes to it. And obviously in real life, 99% of the time, a legitimate client a DNS name would adhere to all these properties and it will contain the same attributes, but since it is controllable by the client, there is always a possibility that someone can malform or craft that information maliciously to mislead the server into doing something that it doesn't want to do, or like in this case, completely compromise the server. This is again what I was telling you about earlier, where proprietary protocols and proprietary clients are involved. One example of this is actually the Oracle libraries and the Oracle TNS listener protocol. Oracle has multiple versions of their libraries available on possibly every platform that they support their database products on, and they expected their database services to be accessed only by, or rather only through these sort of client libraries, and most of the integrity checking and error checking and things like that was actually performed on client side rather than server side, because obviously they didn't expect someone else to come and access it directly, and that led to some serious problems which left their servers completely compromised. The Oracle TNS listener denial of service and the buffer overflow vulnerabilities which were discovered last year is a direct example. And yeah, back to our safe programming issue. A lot of applications today which use object-oriented design principles and object-oriented programming tools tend to create a lot of entities within their code, and it's very structured, it's very nice, and in a perfect world, if something goes wrong, we should be able to clean up all our problems and deallocate all our objects and gracefully terminate, leaving a nice log to the administrators or nice debug information file to be read by any technical support staff or whatever. But the problem is that when an error happens in an application, can we trust the contents of the address space of that process to be reasonably non-malformed to the extent that your post-error processing functionality can take place without actually either being unreliable or leading to arbitrary code execution through the cleanup routines? And in most cases, people don't realize how bad this is, because, for example, if there was a heap overflow and there was enough vtables allocated in the heap for C++ objects, and it'll be very, very easy to actually override a vtable and just override a virtual destructor, which will then be called during your cleanup routine to just make sure that everything is nicely cleaned up, and at that point you'll be owned and it'll be too late. So I have seen some innovative approaches, unfortunately few and too far between, where there has been instances of a parent control application would use another application as just a sort of like a workhorse application under its sandbox complete control, where all the error cleanup and everything was done by the parent program on the child's process by a very innovative way of injecting code into the child's process. So, I mean, it might be overkill, but at the same time, that's probably the only kind of approach which would give you 100% absolute security when it comes to things like this. But at the same time, obviously, I mean, not all the software needs this level of security, so it's entirely dependent on the intended use of the software and how secure do you want it to be. Well, I guess that's about it. So now we are moving on to integer manipulation.
Okay. All right, yeah, as Joey said, now we're going to focus on several conditions regarding integers. Integers are interesting to us because they're often used to store data lengths or calculate remaining space of buffers, both fixed length and dynamically allocated ones. Therefore, if we can manipulate these integers, we're sometimes able to misrepresent how much space is allocated or available for the program to use and trigger a buffer overflow condition. Although the result of these types of attacks are memory corruption in some form or another, they are not your standard buffer overflow. The simple buffer overflow conditions that people talk about usually occur due to failure to account for size at all, whereas integer manipulation is more of a logic flaw, usually exposing some boundary condition that the program has not really accounted for. We're going to really just talk about three things here, which is signed and unsigned integers, different sized integers, and integer wrapping, which is overflowing and underflowing integers, that I touched a little bit before on with str, ncat, and so forth. Okay, now firstly we're going to briefly talk about how integers are stored in a program very quickly. They're usually 32-bit on a machine, but it depends on the machine. We'll assume they're 32-bit here, and they're also implied to be signed, so it can be positive or negative unless the unsigned qualifier is explicitly used. I don't know if you can see that table there too well, but it's just basically a list of the maximum minimum values for 16-bit signed, unsigned, 32 and 64-bit values that integers can take. The limitations and peculiarities of the integer data types can sometimes produce results that were not expected from a calculation. We'll show that these can be used for remote exploitation in a number of scenarios. So I guess we'll first talk about signed and unsigned integers. Often programmers use integers for sizes of data fields or space remaining in buffers, as I said before. If an unsigned qualifier is not explicitly used, then the integer will be signed. This doesn't usually make sense to have a negative length value for something unless an error is indicated by returning -1 from a function. And we can often use this to our advantage. Usually integers can be entered in, negative integers can be entered into a program incorrectly in one of two ways, which is, the first is the protocol in question uses the length specifier controlled directly by the user, which fails to check if the value supplied is less than 0. And the second is a calculation is made based on some user input, which can be affected in such a way to make the result less than 0. When a negative value is given to a bounded copying function, they're often cast to positive values implicitly, which is usually a huge number. This number is often so large, in fact, that exploitation of these bugs can be sometimes quite difficult, but it depends on the target program. We'll sort of mention this a little bit later. But basically, we've got an example here of a sign bug. You've probably seen these a little bit recently on BugTrack and that kind of thing. They're useful, as I said in the previous slide, for evading maximum length checks and stuff like that. The best way I could think of was to show some example code, which you've got there. Basically, the program's getting an integer from the socket and checking if it's greater than 256, and if it is, it's exiting, and if not, it reads it into a buffer. The problem is because the integer is not explicitly declared as unsigned, we can pass a value like -1, and a signed comparison will occur, and the program will think, great, this is like less than 256, we can do the read from the socket and copy much more data into the buffer than in fact we want to. So sign issues are often quite subtle, and holes of this nature have gone undetected for a pretty long time. As can be seen from the example, they're very useful for evading maximum length checks and still being able to send more data than has been allocated. Different sized integers are, as the name implies, integers of different sizes are sometimes used during calculations. Implications of this can include values, 32-bit values being assigned to 16-bit variables, and they can become truncated, and also they can change sign. For example, a 32-bit negative number can become a 16-bit positive number, or a 16-bit negative number can be is not sign extended when it's stored in a 32-bit variable. This might seem really silly, and you think, like, why would people ever do this? But it actually occurs in some major applications, especially in protocols that use 16-bit data length fields, and they're often quite subtle to spot because the 16-bit values are stored in like big structures, and you've got to look at a lot of the code to actually realize what's going on and stuff like that. So we'll move on to integer wrapping. Integer wrapping is basically a class of bugs triggered by causing an integer to go over the maximum boundary or go under the minimum boundary. Basically, the principle here is that, as we showed before, integers occupy a finite space in memory, which is usually 32 bits. And as such, we can only represent a subset of all possible integers. This set is actually quite large and adequate for most programs, but if the user is able to influence that number directly, then the program can sometimes produce unexpected results, leading to remote compromise. We'll consider a few hypothetical examples. The first is an addition problem. As you can see here, a length is received from the network or whatever, and it's probably, the program looks like it's implying that it's about to send a string of that length across the network, so the program allocates the length you give +1 for accounting presumably for null byte, and then mem copies some user data onto that string. If we give the length here as like OXFFFFF, like the largest value, then the +1 will make it exceed the maximum value and wrap around back to 0. So malloc in this scenario will actually allocate 0 bytes. Well, depending on the malloc implementation, it'll allocate some minimum value, usually 8 or 16. But basically, we can then send a lot more data than, or we can try and mem copy a lot more data than is actually allocated. We'll do second is subtraction. This is integer underflows. This is another similar example to the last one, except the program is making assumptions on how much data it just read from the socket, which is basically that it read more than header size bytes. With subtraction, you also saw in action the strncat and stuff like that, where lengths are dynamically calculated, and it is the assumption, for example, with, as I said, with strncat, that size of buffer is greater than strlen buff. So there's that example, and there's multiplication. Multiplication error occurs when 2 or more numbers multiply together with a result larger than the highest possible integer. These occur reasonably often in programs, often when allocating memory which is an array of a data type whose size is greater than 1. Here, this example, if num, the variable num here, is greater than OXFFF divided by size of the object type plus 1, then the integer will exceed its maximum limit and go back to 0, allocating a very small amount of memory and proceeding to copy in large amounts of data, resulting in a buffer overflow. This is all pretty good, but there are some problems when it actually comes to exploiting these that we need to briefly explore, because in a lot of our early work when we were finding bugs of this nature, we found a whole heap of them, but a lot of them turn out to be unexploitable. When determining exploitability of these bugs, we run into problems. Often these bugs cause enormous data copies that we are really unable to exploit. If we return to thinking about the first hypothetical example, you'll recall that an integer could be wrapped by adding 1 to it, the addition example that is. So the memcopy would then, memcopy would then attempt to copy about 4 gigabytes of data, which is going to crash the program once we hit the edge of the segment that our destination buffer resides in. A lot of integer wrapping bugs contain problems just like this one. Also consider stringed up, like I've got there. Like theoretically, a lot of stringed up type routines basically do the same thing as the addition example, where they malloc string length of some string plus 1 and then copy all the data into it. And theoretically, if we could make strlen the maximum representable integer, then we could overflow it. But practically, we can't really do this because we can't supply a 4 gigabyte string. So we end up having one of two problems oftentimes, which is either the program is attempting to copy very large amounts of data, or we need to supply such large amounts of data that it's just not doable. So we've got some solutions. First is the program catching segmentation violations. Sometimes the program catches a sig-seg-v signal and tries to clean itself up. Often these bugs can become exploitable if we corrupt variables or function pointers that are made use of when the segfault handler is called. This is pretty much just what Joey was talking about, where a fault occurs in an application and it tries to clean itself up without, and by doing that it's assuming that its heap or whatever is trustable. The second, again, delivery of other court signals. Sometimes before a segmentation fault actually happens, we can actually trigger other signals that might do something that might be interesting to us. The user may be able to corrupt some variables and then deliver a signal at the right time, which makes use of these variables, like maybe calls free on them or something. And some signals you might be able to send a sig-urge or sig-pipe in a network type situation. Structured exception handling, which has been used a lot on Windows 32 type applications. In Win32, if the stack gets entirely overwritten in large memory copies, an exception is generated, and so exception handling routines are called to help clean up the process, which are located on the stack. And so vulnerabilities of this type on Windows 32 can be often exploited if a large data copy is done to the stack. Cleanup routines, again, stuff that Joey was saying. Sometimes programs contain miscellaneous cleanup routines when the program crashes or exits, especially in the case of object-oriented languages such as C++, which deallocate objects and call destructors and that kind of thing. So we sometimes can use these to our advantages for integer wrapping problems, but the best conditions for integer wrapping bugs do not actually require any of these. They've got the properties that basically an integer supplied is directly controlled by the user for memory allocation or something similar. A loop is entered for the data copy that can be prematurely terminated, and premature termination of the loop does not cause an immediate call to exit, so that we can exploit some cleanup routine. Just a few notes about this integer wrapping stuff. When we were making this speech, we thought that although integer wrapping of some types has been noticed before, the potential threat that these types of bugs represent to the security of software has not really been realized. So we decided to show some real-world examples and quickly show how large applications can be vulnerable to problems like this. Before we show these examples, though, we'd like to point out one or two more ideas we had about when researching this stuff. Firstly, when we talk about firstly, we talk about it as integer wrapping, but it really should be realized what impact this style of bug has on pointer types as well, which are really just integers. Pointer variables that are incremented by large enough amounts could also be made to wrap around to another location in memory, maybe behind the buffer or to another segment. Although this also requires large values, these values will most likely be considerably smaller than what you need to wrap a standard integer, because a pointer may already have a fairly large value like OX, BFFF or whatever for a stack pointer or something. Halvar will be momentarily demonstrating implications that this kind of stuff has on memory allocation routines, which are apparently extremely buggy. Furthermore, we should mention that certain functions are susceptible to being misused if not checked carefully. So like when we were talking about dangerous library functions before, we could add a few, like consider the calloc function, for example, which dynamically allocates an array. A multiplication will be done between the two arguments done to it from memory allocation. So bugs stemming from dangerous use of calloc could arise very easily in the same fashion as the hypothetical multiplication example given earlier. I would also like to note that I didn't really check this out, but it appeared to me that the new operator in G++ seems to internally contain the same type of problem. If you if you allocate an array using the new operator of some data type whose size is greater than 1, and a user can control the amount of data elements allocated, then you can usually cause G++ internally to allocate a very small amount of memory, and then start constructing the objects. I'm not sure at this stage whether this would create an exploitable situation. It depends on the constructors of whatever data type it was that was being allocated. So we're going to go through a couple of real-world examples. I already said that stuff. Briefly, OpenSSH. This is the challenge response bug we published earlier this year. This example has been analysed in BugTrack in detail now, but it's a perfect example of what we're talking about. If you look at the source code of the vulnerable part of SSH, it's actually pretty much exactly the same as the multiplication example I showed earlier. Basically, you can trigger an integer multiplication overflow, which causes an incorrect data allocation on the heap, and we can write past the end of the allocated data with pointers returned from packet get string, which is a routine that gets strings from the network. Basically, the conditions that I mentioned before are satisfied. We're directly able to control an integer that is multiplied passed to a memory allocation routine. We enter a loop that we can prematurely terminate, and although this causes a call to exit, some cleanup work is done before exit actually occurs. And it really stresses what Joey was saying earlier about deallocation routines and stuff actually causing vulnerabilities rather than making the process safely exit, because if they didn't clean up in this situation, it wouldn't have been exploitable. But because they did, it ended up being not only exploitable but very trivial to exploit. So what happened was, it turned out that prematurely terminating the loop, we could override a fatal cleanup function pointer with a pointer returned from packet get string, and basically in OpenSSH they had this fatal cleanup structures which had a function pointer and a pointer to some data that it wanted to clean up. And because we can overwrite the function pointer, what happens is when OpenSSH, the integer overflow actually occurs because it allocates a table of character pointers, and as we're overriding them, it runs out of data in the packet, so there's a premature termination of the loop, which calls fatal, which calls the function pointer, which we overwrite. So when OpenSSH is trying to clean up its various things, it actually jumps directly to the data that we supplied in a string. So we can just put any executable code, and OpenSSH, while trying to clean up, just jumps directly to it and spawns us a root shell. So when noticing a bug like this, it actually, as we said before, with the methodologies you have to follow whether everything is, whether we can actually get to that part of the code, and it turned out it was really easy to do because the options were enabled by default and so forth. But it does stress that you need to check out a program thoroughly because even though the exploitable code was in every single distribution for this particular type of bug and enabled by default, there was a function just before it that needed to return not null, and if it didn't, it wasn't exploitable, and it only returned not null if BSD auth or S key was defined, which is why it only affected BSD by default. So we're going to talk about Neil's example now, which is the one that came out today.
Okay, this example here is the XDR array prototype, which is used in Sun RPC, and this has all the perfect elements of a multiplication integer overflow. If you'll see, we can directly specify the size or the number of elements in the array being transmitted, and a lot of RPC services allow you to transmit unlimited size arrays, so the check for maximum size there is completely bypassed. It then multiplies the number of elements in the array by the size of each element, and that's where we create an integer overflow, and then it goes ahead and allocates the extremely small amount of data. And farther down you'll see that it goes into a loop, a for loop, where it tries to read the number of elements that we specified from the XDR stream, and if it runs out of data within that stream, it'll just return an error condition. So we don't run into any problems with copying a huge amount of data there. Well, just going back to some of the stuff I talked about earlier, if you had actually, I don't know if you had absolutely nothing better to do, if you had checked OpenBSD CVS yesterday or the day before, this was actually patched in this before the advisory went out. So I don't know, people track these things and they can spot these things a little early. I don't think I have the exploit code. Actually, maybe I do. Yes, I do. I'll just very briefly show you what's going on here. The key part of this exploit is the number of elements that you pass to this routine, and you pass a value which is 1/4 of the maximum integer plus some other data. So when it's multiplied, it comes out, the size of the elements are 4, so you multiply it by 4, it comes out as a little bit over the maximum integer value. It's wrapped to a very small value, and we allocate way less data than we should. I think Halvar's up next with buggy memory allocators.
Can everybody hear me? No? Yep. Okay, so let's see whether we get the screen. Okay. Well, around about last year, I was, last year at this time, I was speaking with Chris about auditing or gathering statistics on which library call would be the most frequently used one, and then trying to find a bug in that library call. And well, it turned out we didn't even have to gather statistics because it seems that malloc is among the most used library calls in any application. And malloc frequently handles user inference request sizes, as we've seen. Now, the problem with malloc is that many applications or many large server software implements their own malloc in order to In order to, yeah, okay. In order to, what is this?
It's bad connection. It's probably bad.
Okay, I'll not move. Anyhow, the thing with malloc is, or with these, many applications implement their own heap management in order to speed up everything, like their entire heap management. For example, it is recommended for optimization purposes if you have a large server software or whatever, to generate, well, statistics on the sizes of normal memory allocation in your application, and then optimize your heap management towards, like, well, dealing with those sizes that are most frequently requested. And aside from this, many other applications implement their own memory allocators, and memory allocators have to do arithmetics internally. Two kinds of arithmetics, in fact. They have to do arithmetics on pointers and on integers. Integers being the request size, and pointers being the pointers, well, they have inside their own heap. And memory allocators are really bad. About 60% of them, from my experience, are broken in terms of malloc returning success for stuff like -1. So you allocate 4 gigabytes and it returns success, and in fact allocates like 8 bytes, which is fairly bad. So, well, if malloc breaks, pretty much, well, many other things break, and a broken malloc can open many, many doors. I stumbled across this originally last year when I was taking apart the ball and C malloc implementation because I wanted to exploit an overrun in the heap. And, well, if you allocated -1 there, it would allocate like 8 bytes and succeed. So that's kind of how I stumbled over this. What I would like to do here, okay. What I'd like to do here is a small bug quiz in terms of, well, I've got 7 buggy memory allocators from popular open source packages. I've anonymized those so that nobody really knows what application those are in. And the audience gets 120 seconds to spot the bug in the memory allocator. And whoever does this first will get, like, he will win the name of the package it is in. Okay. Well, can you borrow me your watch? We have a special John McDonald rule, only 1 prize per person. And secondly, the attendees of my training class yesterday may not participate because they might have already seen something of this. In order to win the prize, you have to explain what is going wrong and which values will behave strangely. And if after 120 seconds there's no answer, we will explain the bug, but we will not tell anybody which package it is in. You have to watch. All right? Yeah, what? Sorry?
Those guys over there can't participate either.
Well, they can participate, they're in here, but only 1 prize per person. So, okay, the first one is a really easy one.
Raise your hand.
Raise your hand once you're ready.
Timer.
Down here.
Oh, there's a hand, okay. Yep.
It's simple multiplication. If you pass in 2 outside logs that are big enough, you'll overflow and loop around, and you'll end up with something that's less than X amount of X size, whatever that is. And instead you'll return some interesting number that's actually underflow.
All right, well, that was correct. The trick here is that we have a multiplication in the check, if size times number of items. If you make that wrap around at 32 bits, you'll have a fairly small number. That'll be smaller than max calloc size. And then when the, well, function returns, it'll allocate a way smaller number, and the application will think it has some huge array of structures or whatever, when it doesn't. Okay, you've won a name. Please come to us after the speech. All right, next one. All right, there's a hand down there.
So the size is maxing minus 8 to let
around, we'll call now out of 0, return that.
All right, well, that's it. If somebody gives or feeds a value somewhere between, well, max int minus 8 and max int into this function, they'll allocate, well, minus 1 or whatever you passed into plus 8. So if you pass, I don't know, minus 8 in there, they'll allocate 0 and it'll succeed. If you pass minus 1 in there, they'll allocate 7 and it'll succeed. Yet another name, gone. Okay, next one. Should be fairly easy now. Yep.
Would this be another simple addition one based off of the user supply variable size?
Yes, this is yet another simple addition based on the user value size. Okay, yet another name gone. 3 out of 3, not bad. This one is a little bit trickier. Yes, sir.
I guess it's the alignment minus 1 is like that after that that's negative.
Sorry, again?
Ending with alignment minus 1, whatever alignment is.
Well, alignment would be a value like 4.
Okay.
I think the time's over. Is it?
2 more seconds.
3 more seconds, okay. Oh, yeah.
You can get an overflow on unsigned, because n is an unsigned n.
Okay.
N is very large,
Yes.
then add in alignment minus, go wrap around, and then minus 3 would turn into a negative.
Why would it turn into a negative member? Because it's still being assigned like n. Well, try to explain again. I'm not sure whether I understand what you're saying.
Alignment is 4,
Yes.
n is max unsigned n minus 1.
Okay.
Then when you add that, it will wrap around. The addition will give you a 2.
Yes.
And then minus n3 would give you a negative number.
Will it give you a negative number? I think it should give you a 0. Sorry?
Just round up.
Well,
Depends on how close n is to max n. Max unsigned.
actually, I think, well, this is partly correct. You'll still get the name, but what's happening here is that n is being rounded up to the next even border. Like, for example, or not even, but to the next 4 bytes. So you'll never get a negative value here. But if you pass in like minus 1, they'll round it up to 0. So they round it, and then a 0 size allocation will happen. Well, I think we'll give you the first half of the name. All right. More fun. Jesus, why am I trying to sit this a long time? Oh yeah, right.
if size is very large, then NP is going to wrap. And cause some interesting side effects at that point.
Can you be a bit more detailed on that?
Okay. Basically, if size is very large, then NP is going to actually be less than active first valve, and so then then your if statement will succeed when it shouldn't, and away we go from there. It's hard to say without knowing what a full TD and obstruct T look like.
Okay, yeah, that's good. You will not get in this name, or you can choose between the two names because we only have one price per person. But nonetheless, good work. Anyhow, what's happening here is that we have not an integer which is wrapping around this time, but a pointer. Basically, the end pointer, NP, is being calculated by adding active first avail to size. Now, active first avail is a pointer into the current heap. I don't know what that is under Linux, somewhere at 40 something, like 40 blah blah blah. So any allocation larger than 0 minus 40 will make this end pointer wrap. So this will actually behave incorrectly for a very, very large number of values going in there, not just like -8, -7, and so on, but like for a few million different values, this will not work properly. So if you put a too large value in there, NP will wrap, NP will be smaller than active NP, and it'll just return the first avail pointer, and then corrupt the next first avail pointer, which the next allocation will get. So this is a fairly complex bug. Do we really have 6 out of 6 so far? Okay, well, last one for today, and my personal favorite. This one works. You got it?
Well, so we got the allocation problem, but if the first side is 1, it will generate the divide by 0.
Okay, you sure about that? I'm not sure about that, no, because it divides by round size, and round size will not be 0. So, time's ticking.
Oh, sorry. Okay. Well, the first one is something.
Time's up? Oh, wait. Oh, sorry.
Well, the first thing it's doing is dividing between by round size, but then it's multiplying by round size. So you can still give a very big number in the first slide. You will still wrap around the new first available, right?
Yeah, but what will happen afterwards? Okay, so time's up. I'll explain this for a second. This is a bit trickier. What happens here is the program rounds up the request size to the next even boundary, and then it'll check if request size is smaller than 0. So if you pass in a negative value, obviously this will screw up badly. Well, the trick here more or less is, let me think, oh yeah. Trick here is that you will, well, if you pass in the largest positive value before it passes into the negative one, it'll round up and become a negative number. So size will be negative, but request size is being checked. So request size is positive, and size wraps around into the negative, and then screws everything down there where the new block is issued, and that must have a negative size. So this is a trickier one, and it's one of my favorite bugs. I'll frame it and put it on my wall. Are there any questions concerning this entire speech so far? Oh yes, please.
You mentioned earlier that the automated auditing tools aren't very good at all. Do you see any hope of developing automated tools that can catch the complicated vulnerabilities you talked about here?
No. The question was whether I see any hope of developing code that can automatically detect, well, really complex bugs. And I really don't think that is going to be possible. I think there is a lot that you can do with, like, to find simple bugs, and there's like a lot of potential to write good source code analyzers, which are about a zillion times better than the super grep we have currently. But for the really complex ones, you'll still need a human to look at it and like find the logical flaw. For example, these things where clients are being trusted, or other weird things happened that Nishat was talking about earlier. You can't detect those automatically, I think.
The problem is to not just like detecting the complex bugs, but also determining whether the code paths can in fact be reached. Did everyone hear that before?
No.
Well, the problem is not just detecting complex bugs, but also whether those conditions can actually be triggered by a user or something like that. So even if they could detect some pretty complex type bugs, it becomes really difficult when you're trying to figure out whether a user can actually manipulate values in such a way, like setting flags and having certain characters and stuff like that, to actually get to the right place where that code can be executed. So that's a big problem as well.
That only affects black text. White text don't care.
Oops.
Just fix the down loss. I mean, if you've got buggy code, then just fix it. Don't worry about whether or not it can be reached. It takes too much time to figure out whether it can be reached. You can fix it in less time than it takes to figure out an exploit. So just fix it.
That's up to the software maintainers, I think.
Yes?
With the trusted client-server application, would you also expect to see some light ordering, integer light ordering vulnerabilities?
Well, they don't use NTO. Net2host is short. What's the question? Well, the question was if we have if we have a client-server environment, whether we don't also see endianness problems, probably stemming from the fact that one of the two sides doesn't use net2host short or net2host long. On the one hand, I think those are definitely or could definitely be a source of bugs. Then again, code that has these kind of bugs wouldn't be functional in the first place. So I don't know how many of these sneak through quality assurance, but there's amazing stuff coming out of quality assurance, so you never know. Any other questions? Yes? Well, the quiz will not be posted, I think, but the rest of the thing will. Any other questions? Yes, sir? If you want to, yeah. I might not be able to answer them, but all right. Oops. Well, thanks for being here, and thanks for everything.